Thank you all for coming to today's lunchtime talk in science and math. I will do two brief announcements. One being that next week we have another talk on the mathematics of epidemiology with Dr. Vivas Barber from our math program. And in 3 weeks, something like that, early May, Dr. Weathers will be giving me a presentation on the mathematics of infinity. So, with that, those will be the last two for this semester, and then we'll pick up here again in the fall. So, with that, I'll introduce Dr. Astalos, who will be talking about cosmic silhouettes.
Thank you, Dr. Neri, and thank you all for coming. The reason that I wanted to talk about this topic today is because next month we have an annular solar eclipse happening on May 20th. And then in June we have a very rare event, a transit of Venus across the disk of the sun. And that's going to be the last Venus transit that will happen during any of our lifetimes. Now maybe some of you are more optimistic about your lifespan than I am. But I don't expect many of us are going to live to 2117. So this is the one chance you're going to have left to see Venus move across the disk of the sun. So I want to give a little bit of history, very little on the history side because I'm not a historian, some background in the science, and then I want to get through it quickly so we have time at the end to talk about viewing techniques. How can you actually look at the sun without destroying your eyes and actually see something interesting? So I'm going to start with the eclipse. That's what's happening next month. And historically, there's lots and lots of stories of eclipses affecting human affairs throughout history. There's one that in Wikipedia, at least, it's called the Battle of Halleys, or the Battle of the Eclipse. Happened in 585 BCE. These two states or nations, I don't even know what they called them back then, were battling. And I read the history. It started with an insult, and then someone getting murdered, and then it just escalated. This war had been going on for 5 years when, during this particular battle on, I didn't put the date, I think it's like May 28th, a total solar eclipse occurred during the battle. And both sides saw that as an omen that the gods wanted the fighting to stop. They very quickly drew up a treaty, which included the marriage of the daughter of one leader to the son of the other leader. And they were friends from then on. In ancient China, eclipses were accompanied by the banging of drums and gongs, by chanting. They believed that the solar eclipse was caused by a dragon swallowing the sun. And so they were trying to scare away the dragon and get it to let the sun come back. And in this picture, there's astronomers, the more educated folks, looking at the eclipse casually, and then in the background, the servants, who were, I guess, not as educated, cowering before the gods because they were terrified at this event happening. But there's tons of stories. You can go and look them up and read more of them. They're pretty interesting. What I want to get to is the science of eclipses. So to understand what an eclipse is, you need to understand shadows. Now I'm talking about a solar eclipse, so we're going to look at the shadow of the moon. The Earth's shadow is very similar, though. The sun, being an extended object, shines light at the moon, but back here behind the moon, there are places like here where you don't see light coming from this side, but you can definitely see light coming from that side. So the entire sun's image is not blocked when you're here. This area is called the penumbra. The darkest part, where the entire sun is blocked from your view, is called the umbra, and that's the darkest part of the shadow of the moon. Now, if you're on the Earth and you happen to be in the umbra during an eclipse, you'll see the entire sun blocked out, and that's a total eclipse. If you are in the penumbra, you'll only see part of the sun blocked out, and that's called a partial eclipse. Now, it turns out that that umbra is a cone, and it goes back a certain distance to a point where it ends. And beyond that, in this area, you can see some of the sun all the way around the moon. And that area is called the antumbra. And if you are in the antumbra, this is what you're going to see, is a disk of sun around the silhouette of the moon. Now let's take a look at the geometry from space for a total eclipse. What's happening is the moon is in its orbit. It's passing in front of the Earth. And the umbra itself makes a path across the Earth. And if you happen to be on the Earth at the location where the umbra goes past, you will see a total eclipse. I've never actually seen one, but there is one coming to a state near you in 2017. And so is anyone here who works on the calendar? for the college? It's August 21st, 2017. So I'm going to have some discussions with people. We can't have school starting because we're going to get. I'll show you that later on, though. We're going to get to go see one. But during a total eclipse, the entire disk of the sun is blocked, and you can actually see the corona of the sun, which is the only time you can see the corona is during an eclipse itself. Now, it gets more interesting, as you saw with that penumbra part. Oh, this is a picture taken from Mir back in 1999 of the shadow of the moon, the umbra of the moon, on the Earth's surface itself, so you can see what it looks like from space. Now, the moon's orbit is elliptical, which means at one place, it's closer to the sun. That's called perigee. And at the opposite side, it's the furthest away from, did I say the sun? Yes. The Earth. It's closest to the Earth at perigee. It's furthest from the sun at apogee. And so that means it looks bigger when it's at perigee. It's closer to us. And then at apogee, when it's further away, it looks smaller. And if we look at the range of sizes of the Earth's apparent disk, or the moon's apparent disk, we see that when it's at apogee and it's farther away, it's pretty small, and it's pretty big when the moon's near perigee. When it's closer to us, it'll be larger. Now, the Earth's orbit around the sun is also elliptical, so the disk of the sun is bigger at some times and smaller at other times, depending on how close we are. But the Earth's orbit is not nearly as elliptical as the moon's orbit. The moon's orbital eccentricity is over 3 times that of the Earth's. So the range of sizes, apparent sizes for the sun, is smaller. And it's interesting that if you look at the range of sizes for the moon, it goes from around 29 arc minutes, an arc minute is 1/60th of a degree, up to about 34 arc minutes, whereas the sun's range of apparent sizes is about 31.5 to 32.5, which means when the moon's at its biggest, it can block the entire sun no matter how big the sun appears. But when the moon's at its smallest, it will not block the entire sun no matter how small the sun looks. So that means that sometimes we have total eclipses and other times we have what are called annular eclipses. So if you are in the location of the antumbra as the shadow of the moon goes by, this is what you're going to see. This is called an annular eclipse, and here's another picture of an annular eclipse looking through haze. It's based, that name comes from the mathematical term for that disk. It's called an annulus. It's basically the area between 2 concentric circles. And this is what we're going to have in May. The moon is actually going to be very close to its apogee point. So it's going to be almost as far away from the Earth as it gets when this eclipse occurs. And so there's actually going to be quite a bit of sun showing around the edges. Now, I'll talk a little bit more in a minute about details, where to go and what to see, that sort of thing. But I want to show you, okay, here's the annulus moving. It's just like the total eclipse. When you have an annular eclipse, the annulus moves, or the antumbra moves across the Earth. And if you're in that place, that path, you will see an annular eclipse. Okay, so I'm going to show you NASA's eclipse page. So if you want to get information for yourself about eclipses that are coming up, you can check this out. And there is some neat stuff here. So, go away. Go away. I love Google, yes. Okay. So NASA's eclipse page has lots of interesting stuff. There's pictures you can download. But the neat place I want to show you is down here where it says Decade Solar Eclipse Tables. If you click on this decade, 2011 to 2020, you go to a web page where you get a table showing all the eclipses that are going to happen this decade. So the first column is the date, and if you click on the date, you get a neat picture. So May 20th, 2012, I click on that, and it brings up a neat picture that shows the path of the, in this case it's the antumbra, across the Earth here, and notice it does go through the United States. And then outside the antumbra, you're going to be in the penumbra. This is showing you how much of the sun's disk will be blocked. Now, even if you're just outside of it, say here in Alamosa, we're going to be just outside of the antumbra, still going to have almost 91% of the disk blocked. So it's still going to be a good eclipse to observe from here, although I'm not going to. If you click on the time of maximum eclipse, you get this cool video simulation of, it's really hard to see. There's the moon's penumbra shown on the globe itself, and you can see how it moves across, as well as the antumbra itself. So you get a neat little video showing you, a little animation showing you what it's going to look like. But the best part is if you click on the type of eclipse here, this is going to be an annular eclipse. It takes you to an interactive Google map that has impressed on it the path of annularity. And so if we can, let's see if we can do this. Click on large map. There we go. So you can zoom in, and what you find, zoom in just a little more. Here we go. What you find is in between the blue lines is the path of annularity, which means if you're anywhere inside here, as the shadow goes by, you're going to see an annular eclipse. Notice that Alamosa is outside. So there will only be a partial eclipse here, though a good one. And I'll show you a simulation in just a few minutes. People have asked me if I'm going to be doing anything at the planetarium for the eclipse, and the answer is no, because I'm going to be down here, right about there, for the eclipse. I've been mapping this out. I'm picking my site. There are others who are going to be making the trip as well, so that's where I'm going to be. But I will do something on May 5th. It's a Saturday. There's going to be an activity at the planetarium, the last public program at the planetarium before the renovation. On May 5th, during the day, we're going to be looking at the sun. We're going to be talking about how to observe the sun safely, helping people get ready for the eclipse and the transit itself. So that's coming up on the 5th. Now, I will point out one more cool thing I mentioned. In 2017, where is it? There it is. 2017, August 21st, there's a total eclipse. Let's look at that map. And notice, go away. Notice that it goes right through Wyoming and Nebraska. So I'm hoping, school hasn't started, or I can bribe someone to cover for me, because I would really like to be right around in here on that day as well. But there's the NASA, you can just Google NASA eclipse page, and you'll find that web page and have more information than you know what to do with about eclipses. Now, let's take a look at what it's going to look like from here. This is a program called Stellarium. This is a free open source program you can download and run on your computer. It runs on all the different major computers, Linux, Windows, and the Mac. And it's a planetarium program that lets you see what the sky is going to look like at different times. So we can bring up, that's not what I want. Here we go. The date time window, and it's currently set to today. By the way, I've set the landscape to be Mars because I didn't want the mountains and trees and stuff that the default one has. But we'll pretend we're at the sand dunes. How's that? So this eclipse is going to be on May 20th. So we can jump up 1 month, and then we can go by days up to the 20th. And now we can just drag and kind of move around a little bit. There we go, looking toward the west. And now let's skip ahead a couple hours, and we see the sun heading down. Can you guys see the moon? Yep. So what I'm going to do is get close. Yeah, something like that. And now zoom in a little bit. And there's some neat things you can do. You can turn off the atmosphere. Let's see, there we go. That way you don't get the glow. You can see things a little bit better. And you can click on the sun and say, track the sun for me. So it's going to stay on the sun as I change the time. Now notice as time goes forward, the moon getting a little closer and closer. Let me zoom in a little more. Here it comes. So we're up to what, 5:50, 6 o'clock. And here in Alamosa, which is where this is set for, the eclipse will start around 6:30 in the evening on the 20th. And as it progresses, let me zoom in a little more for you. There's some sunspots in that simulated sun. By the way, today the sun has almost no sunspots. It's really boring. But it's cloudy too, so it doesn't really matter. And so we'll hit maximum eclipse here in Alamosa, somewhere around here. Somewhere around 7:30-ish. And that looks pretty good. I think it's going to be a nice eclipse to observe from here. However, if you want to travel a little bit, whoops, that's not the one I want. I want the location window. Now, Albuquerque, there it is. So here's what it's going to look like if you go to Albuquerque, and let's just skip ahead by a few minutes, and we'll get the annular eclipse there. And you'll actually see the moon cover the center of the disk and have a little bit of the sun showing around the sides. Now, if I continue time here, let's watch the eclipse continue, and all of a sudden, whoa, what's that? You zoom out. I'm zooming out. There we go. Yeah, the sun is going to set while it's still partially eclipsed, both here and in Albuquerque. So that'll be kind of neat to see as well. Okay, so that's what to expect, what you can see. Let's jump ahead now to Venus, or to the Venus transit itself. Is this the right one? Slideshow. That's the one. Okay. So I highly recommend Stellarium. Feel free to download it. It's free. Download it, and it's a wonderful program. Now, there we go. The next thing I want to talk about is a Venus transit, and it's not nearly as spectacular as an eclipse. Now, people have interacted with eclipses for thousands of years. They've seen them, they've thought about them, and it's affected their lives because the moon blocks the whole sun, and of course you're going to notice. But when Venus passes in front of the sun, it's not a very noticeable thing, and most of the time you can't look right at the sun. There is no record of anyone seeing an eclipse, seeing a Venus transit before 1639. Now, it's possible, since a lot of civilizations spent a lot of time looking at the sun, it's possible that people did, especially in the early morning or late evening when the sun is setting and you can look at the sun through hazy atmosphere. It's possible that someone in history saw a dot on the sun, but there is no written record that would indicate that's the case. In fact, there's no record of anyone having seen one transit until Johann Kepler predicted one. Now, Johann Kepler was the guy who got data from Tycho Brahe, the most accurate data before telescopes were turned on the skies, and he used them to come up with 3 laws of planetary motion. And for those of you in my astronomy class, remember those will be on the final. The 3 laws of planetary motion. He used those laws to make predictions about where planets were going to be and so on. And in the late 1620s, he predicted that in 1639, both Mercury and Venus would pass in front of the sun. Mercury on November 7th and Venus on December 7th. And he thought that was such an important thing to watch for that he published, well, he wrote an admonition to other astronomers saying, watch this thing, including some hints, such as start a couple days before this because I might be wrong. He was honest. Unfortunately, he died in 1630. And so his son-in-law, Jacob Bartsch, is the one who actually published this, and it got sent out around Europe. And sure enough, in 1639, astronomers watched, first of all, for the transit of Mercury. And the one that we know of that saw it successfully was Pierre Gassendi. Now, he was shocked. He wasn't sure he was even seeing the Mercury in front of the sun because of how small it is. He expected it to be much larger. Notice, this is a sunspot. This is a multiple exposure of Mercury in transit across the disk of the sun. It's tiny. He first saw what he thought was a sunspot, and of course he didn't see it as it entered the disk. He caught it when it was already in the disk a little. And, okay, there's a sunspot. I can use that sunspot to measure how fast Mercury's moving when I see Mercury. And he realized that sunspot was moving pretty fast. He was like, oh, that is Mercury. So back in those days, we didn't really know how big the solar system was. And so guessing how big will Mercury's silhouette appear was really guesswork. They had their hunch, oh, I think it's going to be bigger than that. And so they were surprised by things like that. Now, that was November 7th, the Mercury transit. On December 7th, I got the dates wrong, 1631. This is 1631. On December 7th, when people looked for the Venus transit, there were some astronomers in Europe who looked. Unfortunately, Kepler's data wasn't quite good enough for him to realize the sun wouldn't even rise until after the transit was over. So the transit was not visible from Europe, so no European astronomers saw it, which doesn't sound good for Kepler. Now, he did predict the Mercury transit successfully, and it was seen, so that was good. But people wondered what was wrong with his prediction. And then this young man, Jeremiah Horrocks, was very interested in astronomy, and he got hold of Kepler's data and his model, and he started looking through the calculations, realized that Kepler didn't make a mistake, he just didn't have very good data on the positions of Venus. So his Venus transit prediction was off by a little bit. Horrocks was able to get some more current or better data on Venus's positions. And so he reanalyzed that data and realized, like a month before it happened, that Venus would transit the sun in 1639. That's where I got the 1639 number. About a month before it happened, he realized it. So, very excitedly, he contacted a friend, William Crabtree, and the two of them planned for observing the Venus transit that no one had ever seen before in recorded history. And he did a good job preparing. He figured out how he was going to set up to observe the sun. He created a piece of paper that had a disk on it, the right size for the image of the sun. He marked it off in degrees and diameters of the sun, and so on. And so he was ready when it happened to be able to just mark the positions of Venus. And he said in his record of this that there was some activity, something was calling, some responsibility that he just couldn't tear himself away from, that he had to look for a little bit, it wasn't there yet, okay, I'm going to go do something, and then he'd come back a couple hours later and look, oh my gosh, it's there. No one knows what it was he was going to. It's suspected that perhaps there were some obligations at church or something. But when he came back, he saw the disk of Venus on the disk of the sun and recorded it and published his observations. So he became the first person to record actual observations of Venus transiting the sun. And he went on and he did more in astronomy. He developed new instruments, he made observations, and then in early 1641 he planned to go visit his friend, William Crabtree, to exchange some data or talk about some idea, and he dropped dead one day. No one knows why. You look up all the records of him and no one knows why he died. The cause was unknown. But he died at 22 years old. Yeah, what a shame. But he went down in history at least. So the next step in our history is going to be, we're going to jump ahead to Edmund Halley of Halley's Comet. Halley observed a transit of Mercury in 1677. And he realized that if we could make observations of these transits at places spread all over the globe, then astronomers could take that data and do something roughly like parallax measurements and figure out how far the sun is away. In other words, through the data of these observations, they could get an absolute measurement of the size of the solar system. Because even then, they didn't know how big the solar system really was. They knew, say, the ratio of the orbital radii. So if you told me that Earth was at 100 units from the sun, then they would be able to tell you that Venus was 72.3 units from the sun. But the question is, what was that unit? What were these actual distances? So Halley had the idea that at the next Venus transit, he didn't want to do it with Mercury because he knew Mercury was so small, the observations were so inaccurate that they wouldn't be able to get the data they needed to measure the distance to the sun. So he pointed at Venus. He said that next Venus transit, which, by the way, Kepler did predict, and it was in I don't want to get the date wrong, 61. So Halley said, 1761, if we get astronomers all over the world to watch that transit in time, we'll be able to make measurements that will allow us to calculate the actual size of the solar system. Unfortunately, in 1761, England and France were at war. And so some of the main European countries really couldn't commit the resources they needed to make successful expeditions around the world. So the observations were not very good. Lots of them just didn't work out too well. 1769, on the other hand, lots of countries put in a lot of money to send expeditions all around the world to make observations of the Venus transit of 1769. So you see that they're spread all over. The best observing place, the longest transit, would have been up here, and so lots of them were up there in Scandinavia, but also people in America. Notice this one here, Baja California, and then one down there. That's, anyone guess what island's down here?
Tahiti?
This would be Tahiti, yeah. Hawaii is a little higher. Here's Hawaii up there. Yeah, so that one's Tahiti. So this is 1769. You don't just like jet off somewhere across the world, set up your experiment, do it, and then jet back home, right? They got on ships and they made voyages that lasted years. It was also very dangerous to travel back then. The one I want to tell you about in particular is in Baja. There was a group from France that went to the southern tip of Baja, California, and they made observations of the Venus transit in near perfect conditions, gathered great data. But a couple days later, a sickness, a disease broke out. and wiped out three-quarters of the local population, killed everyone on the expedition except one person made it home to France, who brought all the data with him. So the data was saved. But it was not a pleasant expedition for most of the people. And then let's get back to, anyone know who went to Tahiti in 1769? We don't have any history professors here? Anyone heard of Captain James Cook? Yeah, and his explorations around the South Pacific. In 1769, he was in Tahiti to observe the Venus transit and make measurements. And he took part in the actual measurements themselves. There's James Cook. And he went on to explore the South Pacific, as you know, until it was in Hawaii, I think, that the locals finally rebelled and he met his end. Now, as far as observing back then, here are some observations. They didn't have cameras. They didn't have telescopes. And they had other equipment that they had designed to make these observations and measurements. But records had to be written by hand and drawn. Pictures had to be drawn. And one of the things you can see from Samuel Dunn's observations from the 1769 transit is here. Notice with Venus just inside the disk of the sun, the edge of Venus sort of smears towards the edge of the sun. This is a real effect. You can see it by eye. You can take pictures of it. It's called the black drop effect. And in fact, as it's entering the disk, entering the disk of the sun, the disk of Venus sort of smears out until it gets far enough that all of a sudden it just, this smeared part just collapses and it becomes a nice sphere, a nice circular disk. As it's approaching the edge of the sun on the other side, at one point it actually reaches out and grabs the edge, so to speak. It smears itself out. It's some kind of strange, weird optical effect. That also makes it clear why it would be difficult to make very accurate measurements of exactly when does Venus enter the disk of the sun. Forget the fact that this was 1769. They didn't have, atomic clocks. They had mechanical clocks that barely survived the journeys to these places and stayed accurate. But even then, even if you had an accurate clock, timing it precisely is very difficult to do because of that effect. There's another effect that you can just see in this picture that's a little strange because Venus has an atmosphere. What happens when part of the disk is still off of the disk of the sun, part of the disk is Venus is outside the disk of the sun, because it has an atmosphere, it glows a little bit. And you can actually see this in photographs taken of the disk of Venus entering the sun. When it gets close enough, you can see the entire round circle. You don't see that with eclipses. The moon has no atmosphere. There's nothing there to catch sunlight and spread it out. You don't see that with Mercury, but you see it with Venus because of its dense atmosphere. So they did make measurements, get observations. They did come up with a calculation for the size of the solar system, and their size was something like 120 million kilometers up to 157 million kilometers, distance from the Earth to the sun. Big range of error. Now, it turns out that the actual range is in there. It's about 150 million kilometers. But still, a lot of uncertainty was in there. Now, when we get to the next series of transits, the next one will be in 1881. Whoa, too far. Oh, sorry, 1874 and then 1882. In 1874, people went all over the world again. Now, in the late 1800s, photography was available. They could actually put cameras on the telescopes and take pictures and time when the pictures are taken, and that way they don't have to, they're not subjected to people's drawings and people's impressions of what they saw. They actually get photographic evidence. Strangely, some countries chose not to use photography at all, and I believe it's probably that, newfangled technology, we don't trust it, we don't understand it, so we'll go with the old tried and true tested technology. The United States did. The United States Naval Observatory sent 8 expeditions for both of the 2 transits that happened in the 1800s. Unfortunately, in the 1874 one, photography, I guess, was not far enough along and the results weren't good enough. The photographic results were just not very clear, and so they couldn't get good data. But then in the 8 years 1882, we sent another one. This is just a picture I found of the people from the 8 expeditions sent out by the U.S. Naval Observatory. And this is just one country. Lots of countries sent out multiple expeditions. They did end up getting, in the 1882 transit expeditions, United States observers alone took over 1,400 good photographic plates. So there was some good data. And then one astronomer spent 20 years of his life studying the data from the 1874 and 1882 transits to try to come up with a calculation of the distance from the sun to the Earth. And he came up with, the number I found was in miles, and I didn't feel like taking time to convert it, something like 92.7 million miles. The accepted value now is around 93 million miles. So less than 1% error, but still not as good as astronomers would like to be able to make precise predictions and things. Now, what's interesting is back in the 1700s, 1800s, these were huge events. The countries were willing to spend lots of money to send people all over the world and take great risk to go and observe. Today, we don't use the Venus transits to measure the size of the solar system. We have much higher tech ways of measuring the size of the solar system, like bouncing radar off Venus. And we have other high-tech ways of doing it. The current accepted value of roughly 149.6 million kilometers has error bars on it of about 3 meters. That's beyond me. I don't understand how they can claim that, but it's unbelievable. So astronomers do not go all over the world to watch a Venus transit in order to be able to measure the size of the solar system. They still do want data on timing, and so amateur astronomers especially all over the world will be observing the transit and timing when the disk of Venus touches the disk of the sun and when it leaves it, and then sending their information to scientists who then use it to incorporate into our models of Venus's orbit around the sun and help make that a little bit more precise. Okay, so there's some history. Now there's some questions you ought to be asking at this point. It's really strange that there were eclipses in 1631 and 1639. There were eclipses in what was it?
42.
I was going to say, that doesn't sound. 69 and 61 and 69? Let's see, that was that one. There we go. 69 and 61. There we go. And then there were 2 in the 1800s, 1874 and 1882. Why is it you get a transit every 8 years apart, and then all of a sudden it's 100 years? And by the way, right now, the one that's going to happen in 2 months is the second of the 2 8-year cycle. There was one back in 2004. So why is that? So I'm going to attempt to help you understand that with a little Mathematica simulation. So what I've drawn here, what I've got, there we go. What I have in the simulation is the sun in the middle, Venus closer to the sun than the Earth out here. It's going to draw a blue line along the line between Earth and Venus. And that, as they orbit, it's going to continue to draw that blue line. I've got a black line drawn across here where they're lined up to begin with. So we're going to pretend that there was a transit at this moment of time, t equals 0, and we're going to watch how do they come back together, how do they reline up. By the way, this alignment is called inferior conjunction. Conjunction is when another planet lines up with the sun. Inferior conjunction is when the planet is closer to us. So what do you suppose they call it over here? Superior conjunction, exactly. Okay, Venus being closer to the sun moves faster. That's one of Kepler's laws, astronomy students. Hope you remember that. So let's start. Whoa. I don't know what just happened, so let's go back. There we go. Let's start the simulation. How about we just get out of that? Maybe that'll help. Okay, so let's start the simulation and we watch Venus take off. And as years go by, whoop, there's a superior conjunction. And now Venus is starting to catch up again. And I'm going to, whoa, stop. Oh, I'm not at the right place. Boom. Let's back up a little. Okay, so what I want to try to show you is it's right about 1.6 years when they've lined up again at inferior conjunction. So if it's 1.6 years to inferior conjunction, when do you suppose the next one's going to happen? 1.6 plus 1.6 is 3.2. Where's the next one going to happen? 4.8. There's superior conjunction. Here comes the inferior conjunction. There it is, 4.8 years. And then there's going to be one more at 6.4. It's an interesting coincidence that Venus's orbit happens to have this connection to the Earth as far as the timing goes. So 6.4 years. And now, what's the next time? 8.0, which suggests they should be back where they started. I can't believe I stopped at that perfectly. Wow. I practiced that in my office, I'll tell you. Notice that we are basically at the inferior conjunction. But we're not, the planets are not exactly right back on the line where they started. In fact, the alignment, that connection of 13 Venus orbits to 8 Earth orbits is not perfect. So the inferior conjunction actually happens a little bit before 8 years, so a little bit before they get back to that original line. And that's going to be important. So we saw that every 1.6 years there's inferior conjunction. Why do we not get a transit every 1.6 years? That I can show you in the next simulation. Here we have a model of the Sun in the middle, Venus, and Earth. And notice that the orbit of Venus in the green is tilted with respect to the orbit of Earth. Now I've exaggerated the tilt a little bit, but I've also exaggerated the sizes of the Sun and Venus and the Earth. And so what I'm trying to show is if there's a inferior conjunction while they're away from, let's bring that down. This red line here, where the planes of their orbits cross, is called a line of nodes. If there's an inferior conjunction out here away from the line of nodes, then Venus either goes above the Sun or below it. It does not pass through the disk. The only time you can get a transit is when the inferior conjunction happens along this line of nodes. Now, in 2004, there we go. In 2004, the inferior conjunction happened with the Earth and Venus right about here, below the Earth's orbit, that plane called the ecliptic. And so since it's a little bit earlier, they're orbiting this way. Since the next one is going to happen a little bit earlier, not exactly 8 years, but a little short, then the one that's going to happen on June 5th, they're going to be up here a little bit. So Venus is going to pass above the center of the Sun. And then the one that happens 8 years after that is going to be too far this way. And Venus, it'll be too high when the inferior conjunction happens, and Venus will pass over the top. So it's only 8 years. There's like two separated by 8 years where you get these transits. And then for the next 8 year and then 8 year, it's above. And of course, all of the lines of inferior conjunction are precessing. So the line of inferior conjunction here, every 8 years, it shifted a little bit. But so have all those other inferior conjunctions. Remember there was one at 1.6 years, it was over here somewhere? Over each orbit here, it's drifting this way. In about 100 years, it's going to line up with this line of nodes. And we'll get 2 transits of Venus. But then it'll drift past, and there won't be another pair of transits for another 100 years until the one that was over here drifts back to this line of nodes. So you can see why this weird connection. There's the transits of Venus go, if there's one here, there's going to be one in 8 years, then there won't be another one for 121.5, I think. And then there's going to be another one in 8 years, and then there'll be another one in 105.5. And then that cycle repeats for a while anyway. In another 1,000 years, we'll only be getting one. Because for you to get 2 in one passage of this line of inferior conjunctions, the first one has to take place just to this side of the line of nodes, so the other one can take place just to the other side. In a couple thousand years, they're going to line up just right where it's going to happen real close to that line of nodes. So the one right before it won't be a transit, and the one right after won't be a transit. So the geometry has to be just perfect. So we're actually pretty lucky to be living when we do and know what we know so we can predict it's going to happen and actually see it. So the question to ask now is, how do we go about observing the transits and the eclipse? So what are the safe ways of looking at the sun when you can't actually look at the sun? Oh, here's the transit, by the way. This is what it's going to look like. In 2012, it's going north of the center. In 2004, it went below the center, south of the center. Universal time seems silly to me because the people in Greenwich, England, aren't even going to be able to see this. So let's use our time. So for here, it's going to start just after around 4:20. It's going to start, and it will go until the sun sets right around 8:20. And on June 5th, we will have telescopes set up outside the planetarium and be able to show people the transit itself. So you're welcome on June 5th to come. That entire time we'll be there showing it off. This one is June 5th. The transit is June 5th. The eclipse is May 20th. Okay, so safe viewing methods for these kinds of things. A pinhole projector. What that means is you punch a tiny, tiny little hole in something, and you point this at the sun, and then you hold up a white sheet behind it. And it actually does create an image of the sun that's passing through that little hole. Now, unfortunately, I don't have anything bright enough to demonstrate it, but it actually does work. You'll get a nice round image, and if there's big sunspots, you'll be able to see sunspots on that image. If you want to make it bigger, make the image bigger, put this up in a window with the sun outside, and then close off the rest of the window with curtains or blankets or whatever to make it dark. And then you can back your white sheet as far away as you want, as far as your room allows, and get a bigger image. The problem is, when you back it away and make the image bigger, the image gets fainter. So you need a dark room to do it. But that is a valid way to do it, and we will be doing this when we're looking at the sun over at the planetarium. It doesn't have to be precise. Here's a picture of a bunch of pinholes, basically light filtering through tree leaves. So these leaves in the tree have filtered the light down to basically just little lines of light getting through. And this is during an annular eclipse. And what you see from each little line of light coming through the tree is a whole bunch of images of the annular eclipse. So you can make one of these easily. You could put 10 holes in this and get 10 images of the eclipse. Or you can go out and find a cool tree and take neat pictures like that. Okay, safe solar viewing glasses. These are cheap and easy to buy off the web. Just make sure that they are the ones that are actually rated for safe solar viewing. I am going to be giving these away at the planetarium on May 5th when we do our program, and again, if we have any left, at the Venus transit as well. And when you use them, just make sure that you actually looking somewhere other than the sun. You put them over your eyes, then you look up at the sun, and when you're done, look down and then remove them. It's really easy to look at the sun and go, wow, that's really cool, and then take them down. And your pupils dilate a little bit because it's dark, right? And then yeah, that's not a good thing. Good, they're good for looking at the sun and safe. A telescope with safe filters, you should never, ever look through a telescope at the sun unless you're absolutely certain that you have safe filters made for looking at the sun through a telescope on the far end of the telescope, the big end of the telescope. Don't get the filters that go over the eyepiece. That's still taking all that light from the sun and focusing it down there where if you get it out of focus a little, it might burn up that filter. This is a fairly cheap one that looks like tinfoil. There are glass ones that are much more expensive, but you'll get roughly the same view. These go on the end of the telescope, and you can look at the sun through it and see sunspots and see planets transiting. We will have telescopes set up with filters on them, so you can safely look through telescopes at these events. Eyepiece projection is where you actually take the filter off the telescope, do it with a small telescope, and you get that white sheet of paper and you hold it up out where the eyepiece is. So here's what it looks like. Here's a small telescope, and there's the eyepiece down here, but rather than looking through it, you just project onto a white sheet. Now put a piece of cardboard over this end, because that image is going to be fairly faint, so you need to block some sunlight. So you have a fairly darkened white sheet of paper to see the image on. And that's a nice, easy, safe way to do it, probably the easiest way of all, or safest way of all certainly too. But when I say easy, I mean even if you don't have a telescope. Oh, I don't have it? Darn. I had a picture I meant to put in here of someone holding up binoculars. They're holding up binoculars to the solar eclipse, and it's projecting images of the eclipse on the ground behind them. And they're just holding, and you get two images. So it's a very cheap, easy, and safe way of looking. And so we'll have this set up as well at the planetarium. We're going to try to have as many of these techniques set up as we can. Finally, point and shoot cameras. When the sun is low, not when it's up high and bright, but when it's getting down toward the horizon and a lot of the light's filtering through the atmosphere, where you're tempted to almost look at it, it's faint enough. I've seen people just hold up point and shoots and take pictures and get an image of an eclipse, of a transit, and Venus shows up. Zoom out as much as you can, put it on a ledge to hold it steady or something to hold it steady, and just take pictures. It never hurts to try. Take as many pictures as you can, and a couple of them may turn out really, really cool. Now, one last thing I want to do is talk a little bit, okay, this is a little shameless self-promotion, but I want to talk a little bit about Zacchaeus Planetarium. I want to point out that in 2014, it'll be the 50th anniversary of Zacchaeus Planetarium. It opened in 1964. Now, it turns out, 2014, with this new grant that we've got, 2014 is the year we're going to be opening the new observatory as well. I think it's a great way to commemorate Zacchaeus Planetarium's 50th anniversary. So look in 2014 for lots of neat events at both the planetarium and the new observatory. Now, I do have a website. I want to make sure everyone is aware that the planetarium has a website. It's one of the blogs that Adams State sponsors, blogs.adams.edu/Zacchaeus. And I have here on the home page, I put up statements about programs that are coming up. Skywatch is the one I really want to show you. It's where I put things about upcoming astronomical events. So here's one on the annular eclipse that's coming up May 20th. The Venus transit, both of which we just talked about. I have some instructions on how to look for satellites that fly by. You can just go out in your backyard where it's dark and watch satellites go overhead if you know when and where to look. So I've got instructions here how to find out. And then I have a list of other events that are coming up that I found, whether they're eclipses, transits. An occultation is when the moon actually passes in front of a planet and blocks it out from view. So there's going to be a Venus occultation in August. Let's see, next year there'll be a Mars occultation, a couple of lunar eclipses, and so on, until finally that total solar eclipse in 2017. So there's a resource for you, the Planetarium's website. Feel free to go there and look for information on astronomical events or happenings at the planetarium. I also want to say I have a sign-up list, an email list for the planetarium. So if you're not getting emails from the planetarium about activities at the planetarium and you'd like to, I have sign-up sheets up here. Feel free after the talk to come up and put your email down neatly, and I'll put you on the list. Thank you. We have about 2.3 minutes for questions. Anyone have any questions? No. Yeah, Steve.
They're measuring that distance from the Earth to the Sun. They're trying to get it very accurate. You say plus or minus 3 meters.
Right, so they can make predictions.
Or something? I mean,
oh, it's average. So yeah, you got to measure. The orbit is elliptical, and so sometimes it's closer, sometimes it's further. They were trying to get a real good bead on the average, which is what's called the semi-major axis of the ellipse. Yep. Anything else? All right. Come on down. You can take a look at some of these things or sign up if you want. Thanks for coming.